Welcome to another lesson on simple circuits. We've already seen circuits built and tested in real life. Now we're going to apply some equations to them. All right, so we're going to look at a couple problems and see how this all works out. All right, the first problem is pretty basic. We're going to start off with just one resistor, all right, and it talks about having a voltmeter. So we see our schematic diagram, which is a circuit diagram. Okay, we know there is the battery, and there is our resistor, and then we have this. And it's saying the voltmeter is 50 volts. So remember what that would look like. We would put the voltmeter from that spot to that spot, and it would read 50 volts, and this thing would be, 200 ohms, all right? Now, we want to figure out the current that is flowing through here. So the current would go through there, travel through the resistor, and then back to the other side of the battery, the other side of the voltage supply. So our main equation still is Ohm's law, which is VIR, all right? V equals I R. Now, our voltmeter gives us the V in VIR. So we have 50 volts. And we're looking for current, which is I, all right? And we know that the resistance is 200 ohms, 200 ohms. So if we had to solve for I, we just use basic second grade algebra. Divide both sides by 200. All right, divide that by 200. And you can see 200 divided by 200 cancels out. And then we have 50 divided by 200. Now that would cancel one of those out. And we see 5 over 20, which is, so I'm going to continue this up here. We have the current is 5 over 20, and that reduces down to 1/4, and then we have the current is 0.25 amps. All right, notice we're just using VIR to solve for that, and we have our answer, 0.25 amps. That's how much current would be flowing through this thing. If you had a resistor with 200 ohms and you hooked up a voltmeter and it had 50 volts, that would tell us that 0.25 amps is flowing through that resistor. All right, let's move on to our next one. Okay, in this problem, we have two resistors that are wired in series. Now, the difference between this problem and our last problem is when our last problem, we just had one resistor hooked up to a battery, all right, and we could figure out how much current it has. But in this one, we have two resistors, and they're wired in series, all right? Notice when they're wired in series, we went over this, it is the same current going through both. Notice in this diagram, there's one current path. The current can't go anywhere else. So it has to stay the same through both of those resistors. All right, and that's one of the ways we identify that they're in series. And the fact that they told us. But that's what the diagram looks like, okay? So the first thing they want to do is figure out the total resistance of the circuit, all right? So how do we do that? So we've seen experimentally that the current goes down when you add in a resistor in series. But the question is why? VIR equation, all right? And if we keep the same voltage, for this to go down, this would have to go up, all right? And the way you can reason that out is, let's imagine we have 1 volt battery and we have a 1 ohm resistor. That means we would get 1 amp of current because 1 equals 1 equals 1. Well, what if we kept that same 1 volt battery, but we had to get this down to a half, right? Because we said we know that the current decreases. Well, what would the resistance have to be? Well, it clearly have to be 2. So now we can see for the current to go down, from 1 to 1/2, Well, the resistor had to go up from 1 to 2. All right. So now if we apply that to our particular problem, all right, we now have to calculate what this new resistance is, all right, because we have two resistors here, and how we work circuits is we always want to be able to work it down to one resistance. This is the easy one. This is one we're good at. So how do we do that if we have two resistors? It's simple. It's simple. Those two resistors that are in series are the same as if, or sorry, could be replaced by just one total resistance. All right. If this is 100 ohms, this is 50 ohms. What could we replace two of those resistors with just one, still have it be the same? So there's a very simple equation that tells us what this resistor will equal if we have those two wired in series. All right, and it's pretty much what you would think it would be. Our total resistance is just R1 plus R2, and you just add them up. All right, so in this case here, we would see if I have 100 and I have 50 ohm resistor, then the equivalent, in other words, the total resistance of the entire circuit is equal to 150 ohm resistor, because you just put one of the resistors is 100 and the other one is 50, and 100 plus 50 and the other 50 ohms. And what that means is this circuit here will function in the same exact way as this circuit here. All right, because you have a 50 ohm and 100 ohm resistor that are in series with each other, and over here you have can be replaced with just one 150 ohm resistor. Okay, so part B is asking for the total current flowing through the circuit. So what that means for us is, instead of dealing with this circuit diagram, which has multiple resistors, we are now able to deal with this circuit diagram. And we know the new resistance is 150 ohms, and it's hooked up to a 30 volt resistor. So we've already seen an example where there's just one. What this means is this resistor, if we hooked up a voltmeter to it, would read 30 volts from that side to that side, because it's the only one there, and it's hooked up to a battery 30 volts. So going back to our first problem, we just use V from Ver, we use our Ver. We can see that the voltage is 30 volts. All right, we're looking for the current, which is I. Our resistance is now 100. Our total resistance is 150 ohms. All right, and we solve for I using simple algebra. The 150 is divided down over there, second grade algebra. 30 divided by 150 is so notice how those zeros will cancel out each other, and we're 3 over 15. 3 over 15, which is 1/5, which is 0.2 amps. So if we had an ammeter hooked up to this thing right here, all right, or right here, we would see that that thing would read 0.2 amps. All right. Now, if I had to add in another resistance here, we know that the overall resistance would go up because I'm adding in a resistor in series. All right, I know this because it's all the same path. So therefore, the current would go down, assuming, I kept this at 30 volts still. All right, and that's how we handle resistors in series. Okay, let's move on to our next problem. Now we have a problem with resistors that are wired in parallel, okay? And we have a 20 ohm and a 30 ohm. There's our 20, and it doesn't matter which one's on top, which one's on bottom. 20 ohm and 30 ohm resistor. And that's what the diagram will look like, all right? So we can recognize this a couple different ways, but maybe the easy one here is we can see the current is going to be flowing along these wires, and when the current gets to here, some of it will go that way and some of it will go that way. And one of the part B is asking, well, what are those two currents? All right. Well, we're not even sure. We don't even know what this current is right now either. We do know that this is 10 volts. But if you think back to our Ohm's law, well, our simple circuit lesson when we built these things, when we took a voltmeter, all right, and touched it to the two spots that it was hooked up, if I took a voltmeter and touched one of the probes there and one of the probes there, all right, we know these things would have the same voltage. And in this case, this is kind of the key here, notice that these 2 points are hooked up directly to 10 volts. So they would actually get 10 volts. We'll talk about that in a sec. All right, we'll come back to this. This is where it gets pretty complicated. So we deal with the first part A, what is the total resistance of the circuit? We can't just add them up because that equation that we did before for the R total is when they were wired in series. It's a little bit different for parallel. And we know it's different for parallel because when we built those circuits in real life, we saw that we got different results. So that means that something else has to be modeling resistors that are in parallel, all right? And so that equation, if you look it up on Google or in a book, they will give you a more complicated version than what I'm going to show you here, all right? It involves adding fractions and inverse fractions, and I've seen most people's math skills, and adding fractions is not a skill that a normal person has. I can do it no problem, but I am not normal, all right? So I'm going to make it easy for you to so you can avoid that math problem and still be able to work simple circuits, all right? So our resistance equation for resistors that are in parallel, all right, is just this. You multiply them, all right, R1 times R2, and then you divide by the addition of them, R1 plus R2. All right, so if we apply this equation to this problem, you can see we have 20 times 30, that's the first resistor and the second resistor, divided by 20 plus 30. And that means our R total, all right, equals 6 with 2 zeros on top over 50 on the bottom. We'll cancel out that 0, and 60 divided by 5, I believe, is 12 ohms. Now, here's what's interesting about resistors in parallel. All right, notice when we did this, we had a 20 and a 30, and our total resistance value was less than both of them. All right. So if I were to add another resistor in here, if I added a resistor that had 1,000 ohms to this problem here, if I put it wired into parallel, that would still be less than 20, all right? Parallel resistors are a little bit counterintuitive. You add resistance in, and the total resistance actually goes down, all right? And this equation shows that happening, all right? So remember, whenever you add calculate the total resistance of resistors in parallel, the total resistance that you end up with here, the total resistance you end up with is always less than either one of these, is always less than the smallest one. So if I took a resistor that was 1 ohm and a resistor that was 1,000,000 ohms, and I wired them together in parallel, the total resistance of that circuit would be less than 1. All right, it's always less than 1. Resistors in parallel, the resistance goes down. Now, I've been saying that it comes across as counterintuitive. When you add in resistance, you can actually lower the resistance. But we've already seen this in real life. We saw that when we added resistors in parallel, we actually got more current. Well, what we just saw is proven if we go back and look at Ver, all right? So we know if the voltage stays the same. If the current goes up, then we have to get the resistance to go down. In other words, if the voltage is 1, the current will be 1 when the resistance is 1. All right? Well, we keep the voltage the same at 1, and the current went up like we did in our experiment, then that would have to mean that the resistance would go down and half is lower than 1. All right? So we've seen data, and we've seen an experiment of this actually happening. All right? So let's move on to our second parts here, part B and part C. Part B wants to know how much current is flowing through each resistor. So what they're asking for here is, okay, the current's going to come here. Now we can see the current has to split up. Some of it has to go this way, and some of it has to go that way. Well, this question is asking, well, how much of that current went here? How much of that current is going through here? All right. So how do we do this? If you remember back to our simple circuits, we found that, and what I showed you before, is that both of these are wired up to the same spot, there and there. And those two spots had the same voltage as that. All right? So you can think of it like this. All right, now that we know how to, the total resistance, those two resistors can be replaced by the total resistance, which we found out was 12, all right? And we've done this problem a million times now. We know that this 12 ohm resistor is just hooked up to 10 volts. So the key here, it's kind of tricky, those two dots are the same as those two dots. And if those two dots are getting 10 volts, then those two dots are getting 10 volts. And if we go back, we know that each one of these things have the same voltage. That was one of our highlights, is that resistors in parallel get the same voltage. That's a pretty big key. The resistors in parallel get the same big voltage, and that's different. That's different from things in series. Resistors in parallel get the same voltage. So the fact that when resistors are in parallel, they get the same voltage, that allows us to apply VER to each of these things individually. All right, to each of these, make some room here. All right, and if we apply VER for the top one, V equals IR, we know this one is hooked up to 10 volts. We don't know what the current is, that's what we're trying to figure out, and that one's resistance is 20. All right, and we divide the 20 over, 10 divided by 20 gives us 0.5 amps. And then we can do the same thing down here, all right? V equals IR. The voltage this one hooked up to is 10 volts. 10 volts, because it's the same as the other one in terms of volts. And we're looking for the current, and we know the resistance, is 30 ohms. 30 ohms. And now we see we divide this 10 volts by 30 ohms, and 10 divided by 30 is 0.33 amps. All right, and that's how much current is going through each one of those individually. This one gets a different current than what this one's getting. Now, for part C, there's two ways to do this, and I'm going to show you both of these. All right, we already know that these are an amp, half an amp, and this 30 ohm is going to get 0.33 amps. So if the current goes here and some of it goes there, some of it goes there, that means that when it comes back down in here, they're both going to have to combine. So the total is just 0.83 amps. We can just add those two up. Over here, we'd have 0.3 amps going into this. So it would split off, doesn't split off equally in this case. Half 0.5 amps go there, and the other rest 0.33 amps go there. And finally, the other way to complete this last part is just to do VER. We know that these two resistors can be replaced with this. We know that these two resistors, all right, and we can see that 12 ohm is hooked up to 10 volts. So we can just apply our trusty VER equation. V equals IR. We know the volt. We know we're trying to find the current. Our total resistance is 12, and 10 divided by 12 gives us 0.83 amps, which is good because that's what we solved for the other way. All right, and that's how we deal with circuits without building them, trying to figure them out without having the need to spend the equipment and the time to build up a circuit, and we can figure out what would happen without the need to build all these things.